Welcome back to Physics 142 online. We're moving now from the part of the course dealing with waves and light and properties of light into the section where we start talking about electric charges, forces, and fields. And this first section is a rather long one, encompassing 2 chapters from the textbook. We're going to start off with a review of some fundamental properties of charges and how they interact with one another. And always remember, problems worthy of attack prove their worth by hitting back. So, a couple of properties of charges that you're probably well familiar with, that some of which date back to the time of Benjamin Franklin. First of all, unlike mass, charges come in 2 fundamental types, and we call these positive and negative. And experiments show that opposite charges attract one another, while like charges repel. We also know that charge fundamentally is a conserved quantity, that whatever happens in a reaction, whether that's a chemical or a nuclear reaction, the total amount of charge before is equal to the total amount after. Finally, charge is quantized. There's a fundamental quantity that if we break charges up into smaller and smaller pieces, you can't get smaller than a certain quantity. So all charges in nature that are free charges have this quantification, where the total charge, the symbol Q is what we use for charge, is equal to some integer multiple of a fundamental charge E, where E is 1.60 times 10 to the minus 19 in units of coulombs. And so this is the fundamental charge on either a proton or an electron. And of course, for the electron, the charge is negative. Coulomb's law is an expression that tells us how charges interact with one another. If we have 2 charges Q1 and Q2 separated by a distance r, Coulomb in 1789 provided the first experimental evidence for how the force between these charges depended on distance. And he found that the magnitude of the force was proportional to the product of the charges and inversely proportional to the square of the distance between them. And this actually looks quite similar to the force law that Newton found for masses through interacting through gravity. This K is simply a proportionality constant that has the value that it has because of the unit systems that we choose. But it has a value that's actually quite large in units of Coulomb squared per Newton meter squared. And it governs the strength of the interaction between charges and the fundamental strength of the electromagnetic force. Coulomb actually did this experiment. It was quite a difficult experiment because when you charge an object up, depending on the humidity of the environment, the charge tends to leak off because water molecules that are in the air collide with the object and tend to make charge bleed off. And as a result, it's difficult to do experiments quickly enough so that you can assume the charges that you're working with stay constant. But Coulomb was able to do this and showed on the basis of 3 data points, indeed, that the force between those charges was proportional to 1 over the distance squared. Now here's a section that I'm going to wait and talk about in class, having to do with the value of that fundamental constant that governs the strength of the electromagnetic force. So here's an example where we actually use Coulomb's law to calculate the net force on a charge due to 2 other charges. So imagine this charge configuration where we've got a positive charge on the positive y-axis, a negative charge at the origin, and then another negative charge on the x-axis. And the distances shown are 2a along x and a along y. So we'd like to find the net force on the charge at the origin, the negative 2q. And we have to remember, of course, that force is a vector. And so if we want to find the net force on the charge at the origin, we have to sum up the forces that it feels due to the 2 other charges. So let's draw those in as vectors. We'll see, of course, that the plus charge on the positive y-axis pulls upward on the negative charge. Since they're opposite, they attract each other. So we'll have to calculate that force. And then there's a repulsive force that the charge at the origin feels because the charge on the x-axis is also negative. So those two forces, if we can calculate those, and we'll use the unit vector notation that we learned how to use earlier in the course, and we'll just add those two forces together. So the force acting along the positive y direction has the magnitude given by the Coulomb constant times 3q 2q over a squared, and that's in the j hat direction. Then there's going to be a force in the negative I hat direction given by k 2q 2q over the distance 2a squared. The minus sign takes care of the direction, that's along I hat. And so when we simplify, we find that our net force has a positive y component and a negative x component and would be pointing upward and to the left from the origin. Now, in talking about the force between objects that carry electric charge, a question arises because there's a little bit of a difficulty trying to envision how these charges exert forces on one another. How can they transmit forces over empty space, whether those are attractive or repulsive forces, without actually being in contact with one another? And Newton faced this same kind of question when he came up with his law of universal gravitation back in the late 1600s. All the forces that were known at that point were assumed to act through contact between the two objects that were carrying the forces. And so Newton didn't have a good idea of how that worked. He just said that it worked and did not really have an explanation for that. So Michael Faraday, who was a very talented experimental scientist in the 19th century, he was the first one to propose the idea of the existence of lines of force spreading out in all directions around an electric charge. And he thought of these lines of force, which we couldn't see, but the effects of which you could measure. He thought of these lines of force as causing a charge to act on another charge. So this was not really a very highly mathematical explanation when Faraday first proposed it, but it became the basis that others used for the idea of an electric field surrounding the space around a charge. And so this electric field is the way that one charge can act upon another charge that is in the vicinity without actually coming in contact. And this notion of a field connected with a particular force is a very rich one in physics. So let's define it. How's the electric field defined? Imagine that we have a positive charge plus Q, and the field lines are defined in such a way that they point in the direction that a positive charge would feel a force at that location. So imagine a small test charge, Q0, and it's positive, and we put it at a certain point in space. Whatever direction it feels the force, that's the direction of the electric field at that point. And here we're talking about the electric field due to the charge plus Q that we started with. And so we can define that electric field quantitatively as the force that that test charge would feel, if we could measure it, divided by the test charge itself. And so it becomes a property simply of the point charge plus Q and not a property of the test charge. The test charge is just used, in fact, as a kind of detector of this electric field. So according to this definition, the field lines, as I said, point in the direction that a positive charge would feel a force. And now we can go back and use Coulomb's law to find an expression for the electric field of a point charge. So if the electric field is F over Q0, well, the F is K times Q0 over R squared. So multiplying that by 1 over Q0 gives us this result, where we've used R hat to indicate the radial direction pointing in space away from the location of the positive Q charge. KQ over R squared gives us the magnitude, R hat gives us the direction. So, units of electric field, because it's defined as force per charge, those units are newtons per coulomb. And we could write down the newton right in terms of kilogram meter per second squared, but the electric field is often quoted in units, newton per coulomb. Now if we want to draw electric field lines in a systematic way, there are rules for doing this. These are not a very large emphasis in this part of the course, but if you want to actually draw the field lines in a way that's consistent, there are simple rules for doing that, And rather than work through the rules right now, I'll just show you a couple of examples of the results. Because having these electric field lines and being able to understand what they mean is helpful in looking at the properties of collections of charges. So imagine that you have a positive and negative charge that are equal in magnitude and separated by a certain distance. The direction of these arrows always points, if I were to drop a charge down into this region between the two charges, the direction of the field line with the arrow shown is the direction in which a charge would feel a force. So you can see near the negative charge and near the positive charge, they look like the field of a point charge, because close to those two, you would see very little effect from the other charge. But for example, in between the two, if we were right smack in the middle, a positive charge would feel a repulsive force from the right and an attractive force from the left, and so it would have a net force pointing to the left. So these field line diagrams are actually quite useful. Now imagine a little more complicated situation if the positive charge here on the left was twice the magnitude of the negative charge. So the symmetry associated with the equal dipole diagram is lost, but the way that this is made quantitative is to show that there are twice as many field lines emanating outward from the positive charge as there are coming into the negative charge. The other field lines that don't come into the negative charge go off to infinity in various directions. So, one last thing then, our definition of the electric field allows us to write down an expression for the force that a charged particle feels when it's in the vicinity of an electric field. So we're not worried right now about what generates this electric field, but imagine that we have an electric field in space indicated by the direction of the arrows with a magnitude equal to E, and then we drop into that vicinity a positive charge Q. So what would the force be that it feels? Well, the definition of electric field is force per unit charge, and so if we have an electric field to start with, and there's a charge Q that comes into its vicinity, the force is just Q times E. So be careful, because the Q can either be positive or negative in this equation. If this is a positive charge, it will feel a force along the direction of the electric field. However, if it's a negative charge, it will feel a force opposite to the direction of that field. And here's the point where we connect our study of electricity with our study of mechanics. If we have a knowledge of the electric field in a region of space, then, knowing a particular charge magnitude, we can calculate the net force. And after that, it's a simple matter of mechanics to calculate the acceleration of a charge, if it's got a certain mass, and then, from the acceleration, to be able to calculate the velocity, and from the velocity, the position. And therefore, we would be able to determine its overall motion as a function of time. So, since that's the goal of mechanics, being able to calculate the motion of an object as it experiences various forces, in the next few weeks we're going to spend a lot of time learning how to calculate the electric field in a certain region around various kinds of charge distributions. Because if we know how to calculate the electric field, it allows us to calculate the force that a charge feels, and then to use all of the apparatus of mechanics to find the motion of that charge. With that introduction, I will see you in class.